Now chapter number 13, nuclei. See, in previous chapter we discussed about structure of atom, and in that we discussed this thing, almost entire mass, 99.9% mass of the atom is concentrated in the small tiny region at the center, which is known as nucleus or nuclei. As well as the entire positive charge of the atom is also concentrated in nucleus. Okay. Then scientists thought like this, whether nuclei have internal structure like atom. So in that particular direction, when scientists carried out detailed studies, then they came to know about so many things related to the structure of nuclei. And in this particular chapter, we'll discuss something about the structure of nuclei, means about the constituent particles in the nuclei, as well as the interactions between those constituent particles. Now, the atomic mass, that is very small one. Okay. Now here we use another unit to represent the mass at atomic or nuclei level. And that particular unit which we use, that is called atomic mass unit. It is represented by small u. And see its definition. So atomic mass unit, or 1 U mass, that is the mass equal to 1/12 part of mass of carbon atom. Now see, we know mass of carbon atom, that is 1.99267 into 10 raised to minus 26 kilogram. Now take 1/12 part of it. It implies that divide this mass by 12. So we will get 1 U mass. 1 U mass, that is mass of carbon 12 atom, divided by 12. So we will get 1.99267 into 10 raised to minus 26 by 12. And now finally, we'll get 1 U, that is 1.660539 into 10 raised to minus 27 kilogram. This is 1 U mass. It is known as atomic mass unit. So this one is the convenient unit to represent mass at atomic and nucleus level. And in nature, we can observe this thing. If we take the mass of the lightest nuclei, that is hydrogen. So the mass of hydrogen atom, if we consider, then for so many elements, the masses in terms of U are in the integer multiple of the mass of hydrogen atom. No doubt some exceptions are there. Okay. So here, if we think about the periodic table, then in that we can observe this thing. Some elements have the species for which the chemical properties are same. Means they lie at the same place. They occupy the same place in periodic table. But their masses are different one. So these type of species of the element are known as isotopes. Even the lightest one, hydrogen, also have isotopes like deuterium, tritium, like that. Okay. And in the formation of that particular element, the composition of these isotopes are different one. Suppose we take one simple example of chlorine. Now, Mass of chlorine, that is 35.46 U. It is not in the integer multiple of mass of hydrogen atom. But chlorine have two isotopes. So say these two isotopes of chlorine are with different composition in the formation of chlorine. Say, suppose we think about its two isotopes, then one isotope have the mass that is 34.98 U and another one have the mass 36.98 U. But in the composition of chlorine, the isotope with mass 34.98 U, that is 75.4%. And the isotope with mass 36.98 U, that is 24.6%. So we can say these are the compositions of isotopes in the element. So if we calculate the average mass of chlorine by taking the compositions of these isotopes, then we can write 75.4% means 75.4 by 100 into 34.98 U plus 24.6% means by 100 into 36.98 U. So resultantly we can write 75.4 into 34.98 plus 24.6 into 36.98 by 100. And we'll get 35.47 U, and that is the atomic mass of chlorine. Clear? So in this way, the elements have the compositions of isotopes in the formation of it. Clear to all of you? Now see, here when we represent any element at that time, first we think about its atomic number, which is represented by symbol Z. That represent the number of protons in the nucleus, or we can say number of electrons in the atom, because atom is electrically neutral. So obviously the number of protons and number of electrons will be identical one. But say here, if we think about the isotopes of hydrogen, right? Hydrogen, deuterium, tritium. So here all have one proton in the nucleus. But if we think about the masses of all these three, then masses are in the ratios 1:2:3. Only one electron is there. Mass of electron, that is very small. It is 0.0055 U. Okay, so it is very less compared to mass of proton, and therefore we say almost entire mass that is concentrated in the nucleus. If we take the mass of proton, then mass of proton, that is 1.00727 U, and mass of electron, that is 0.0055 U. Okay, but if we think about the mass of hydrogen to deuterium to tritium, then it is in the ratio 1:2:3. Clear? It implies that definitely some other electrically neutral particle is there in the nucleus. Scientist Chadwick performed the experiments related to the bombardment of alpha particle on the beryllium, and he studied about the emission of the neutral radiations. But if we think about the energy of those emitted neutral radiations, then in those days it was termed as photons. But if we carry out the calculations related to the energies emitted here and the obtained energies were not matched. So by using law of conservation of energy as well as law of conservation of momentum, Chadwick represented this thing finally. This emission that is nothing but of neutral particle, and that particular neutral particle was named as neutron. And for this discovery of neutron, Chadwick got Nobel Prize. Okay. So mass of neutron, that is very close to mass of proton. It is slightly heavier than proton. Mass of neutron, that is 1.00866 U. Okay. So in terms of kilogram, if we take mass of proton, then that is 1.67262 into 10 raised to minus 27 kilogram. And for neutron, it is 1.6749 into 10 raised to minus 27 kilogram. Okay. So discovery of neutron was made. So then it was clear now in nucleus, protons which are electrically charged, which possess positive charge, and neutrons which are electrically neutral resides in the nucleus. So we can say these are the constituent particles of nuclei. Clear to all of you? Now, how the nuclei of any element is represented? See, the atomic number, that is Z, that gives you the number of protons in the nucleus, and capital A that we use for atomic mass number, that gives you the total number of nucleons. It implies that the number of protons plus number of neutrons in the nucleus. So if you take A minus Z, then that will give you the number of neutrons in the nucleus. Now, how symbolically the nuclei of any element is represented? So, see here, this X, that is the symbol of the element as per periodic table. As per periodic table. For hydrogen, here we have to write H for carbon, C for helium, He, like that. Okay. Then Z and A, that we have to represent as written on the board here. Either you can represent the element nuclei symbolically as ZXA in this manner or ZXA in this manner. Clear? We already discussed Z represent atomic number, that is nothing but the number of proton in the nucleus. We are studying about nuclei, so we are interested in number of protons. Otherwise, it will give you number of electrons also. In chemistry, majority you use this symbol for number of electrons also. Clear? And A, that is the total number of nucleons, that is nothing but the number of protons plus number of neutrons, and that is atomic mass or atomic mass number. And if we take A minus Z, that is capital N, it is number of neutrons in the nucleus. So in this manner, the nuclei of any element is represented. Clear to all of you? See, for elements, if Z that is the same one, but atomic mass that is different one, then obviously N will be different one. Then those are known as isotopes of elements. Okay. Then if for the species of any element, Z is different, A that is same one, obviously N will be different one, then are called isobars. Now, if Z is different one, A is different one, but number of neutrons that is same one, then it is called isotons. And if Z, A and N all are same one, but radioactive properties are different one, then those elements are known as isomers. You have to remember this thing because they can ask you the short question like this. They will give you the different elements, 4, 5, 6 elements, and then they can ask you about the pair of isotopes or pair of isobars or pair of isotons in the given elements. Like that, they can ask you the question. Clear to all of you? Then after, the size of the nucleus. See, no doubt, in last chapter, we discussed this thing. The radius of the nuclei, that is of the order of 10 raised to minus 14 to minus 15 meter. With the help of the experiment of alpha scattering by gold foil. But what is the exact or accurate radius of the nucleus? And no doubt, for different nuclei, this radius will be slightly different one. So, how to calculate this radius accurately? Because see, in the experiment of alpha scattering, if we consider that alpha particle in Geiger-Master experiment, we discussed this thing. The alpha particle bombarded on the gold foil was with energy equal to 5.5 MeV. 5.5 MeV. But suppose we take the energy of these alpha particles that is greater than this one, then we get some less distance of the closest approach compared to the distance of closest approach obtained in this experiment performed by Geiger-Master. So actually here in this particular experiment, the results and the calculations all based on Coulombian force, right? But when scientists carried out somewhat detailed study related to the size of the nuclei, then they observe this thing. It depends on, no doubt, number of nucleons in the nuclei. So, finally, the radius of the nuclei with atomic mass number A calculated as R equal to R0 A raised to 1/3. Where R0 that is the constant and its value that is 1.2 into 10 raised to minus 15 meter, that is 1.2 Fermi. So, radius or we can say size of the nuclei that depends on the atomic mass number means total number of nucleons residing in the nucleus. Clear to all of you? Now, see, we already discussed this thing. Almost entire mass of the atom is concentrated in the nuclei. So, depending on the mass and the size of the nuclei, if you calculate the density of the nuclei, then that is almost equal to 2.3 into 10 raised to 17 kilogram per meter cube. It is almost constant for all nuclei. Tremendous large one. See, what is the density of water? That is 10 raised to 3 kilogram per meter cube. This one is of the order of 10 raised to 17 kilogram per meter cube. It implies that the density of nuclei, that is approximately 10 raised to 14 times larger than that of water. So from this one can understand easily this thing. What a closed pack structure is there in the nuclei. Clear to all of you? So this particular equation was derived with the help of the experiment of scattering of fast electrons bombarded on the different nuclei. Okay. Then after example 13.1. Given the mass of iron nucleus as 55.85 U and A, that is 56, then find the nuclear density. Okay. Now see, mass of Fe, that is given to you 55.85 U. So first convert it in kilogram. So 55.85 into 1.66 into 10 raised to minus 27. Finally, you will get 9.27 into 10 raised to minus 26 kilogram. A, that is given to you 56. Now we know this thing. Density, that is mass upon volume. So nuclear density for iron, that is mass of Fe upon the volume of nuclei, that is 4 by 3 pi r cube. But r, the radius of the nuclei, that is r0 into a raised to 1/3. We discussed. So this is equal to mass of Fe upon 4 by 3 pi into r0 a raised to 1/3 whole cube. So we can write 3 times mass of Fe upon 4 pi. Now r0 cube and a raised to 1/3 raised to 3. So you will get A. Clear? Now substitute the values. 3. Mass of Fe 9.27 into 10 raised to minus 26 upon 4 pi r0. R0, that is 1.2 into 10 raised to minus 15. That is the constant we discussed. Cube of it, and A, that is 56. Now substitute these values and calculate it. You will get the answer. Clear? Then mass energy and nuclear binding energy, that is the topic. In that, first we have to discuss mass energy relation. See, initially it was believed in any type of reaction, energy is conserved as well as mass is also conserved, but this conservation of energy and conservation of mass takes place independently. But then after scientist Einstein represented this thing, mass is a form of energy. Okay? And independently mass and energy are not conserved, but jointly mass and energy conserves in the reactions. Mass and energy are associated with each other by the relation E equal to mc square, where c, that is the velocity of light in vacuum, its value, that is 3 into 10 raised to 8 meter per second. So here, mass when converts into energy, then the energy obtained, that is equal to m into c square. That is equal to m into c square. So if we calculate the energy equivalent to mass 1u, then we can calculate it like this: E equal to mass that we take 1u, means આપણે એવું કેલ્ક્યુલેટ કરવા માંગીએ છીએ કે 1u માસ જ્યારે એનર્જીમાં કન્વર્ટ થાય તો કેટલી એનર્જી મળે આપણને, right? So we can say E that is equal to 1u mass into c square, 3 into 10 raised to 8 whole square. But 1u mass, that is 1.66 into 10 raised to minus 27 into 3 into 10 raised to 8 whole square. So when you solve this one, you will get 1.4924 into 10 raised to minus 10 joule. Divide it by 1.6 into 10 raised to minus 19, you will get 0.9315 into 10 raised to 9 electron volt. Divide this 10 raised to 9 into 2 per 10 raised to 3 into 10 raised to 6. So 10 raised to 3 into this one, 9.9315, that you can write 931.5 into 10 raised to 6 electron volt. 10 raised to 6, that is mega or million, we can say. So energy E, that is 931.5 MeV. It implies that we can say 1U mass, that is equivalent to energy 931.5 MeV. Clear to all of you? Example 13.2. Calculate the energy equivalent of 1 gram of substance. So mass, that is 1 gram, that is 10 raised to minus 3 kilogram. Energy equivalent to it, that is mc square, mass, that is 10 raised to minus 3 into c square, that is 3 into 10 raised to 8 whole square. So 10 raised to minus 3 into 9 into 10 raised to 16. Finally, you will get 9 into 10 raised to 13 joule. If you want to give answer in terms of electron volt, then divide this one by 1.6 into 10 raised to minus 19. You will get answer in electron volt. Or you can represent that one in terms of MeV also. Clear? Or directly you can calculate this one like this also. 1U, actually 1U, that is 1.66 into 10 raised to minus 27. So see, in this theory we discussed 1.66 into 10 raised to minus 27 kilogram is equivalent to 931.5 MeV. Then 10 raised to minus 3 kilogram is equivalent to how much energy? With the help of simple unitary method also you can calculate this one. Clear to all of you?